Okay, good morning. So today I'm going to talk about chapter one, and we actually started parts of chapter one last week, and I hope you have bought your textbook already because you should be reading along these chapters. And this week I'll cover the rest of chapter one, and we'll continue with SM 51. And some of you saw little mistakes. Yes, I'm glad you tried it, and this week I'll have the corrected version to show you. And so this is chapter one. Basically, it covers what the OSs do, system organization. A lot of it is really review from computer architecture. And so these things should make sense to you. If not, you should learn quickly. A lot of these architecture concepts, we may not cover all of them, but you should know the terms because they are closely related to what operating systems do. And so there are all these things. This is really just an overview, and we'll have a chance to cover the different topics over the course of this semester. So a computer system, you should think in terms of the users, applications, and the OS is really part of it that supports the use of a computer system. And who it supports, well, it depends on what you mean by user. User doesn't have to be a real person. User can be another computer system, could be a developer, right? It doesn't have to be the end user. The end user is only one of many possible kinds of users. And so some of the support you see OSs do really are aimed at helping programmers to have an easier time writing programs or writing application programs possibly, and sometimes writing system support programs. Now applications are really the program code that solve problem really for the user, on behalf of the user. They use system resources, so you know about, sometimes for mobiles they're called apps, right? Word processor, compilers, browser, database, games. But some of them are used so much by other programs as well, they are kind of factored out and moved to the system side. And so there's always controversy as to what do you consider part of OS and what's not part of OS. Right? There's certainly contentions, and there's been lawsuits going on with like Microsoft a couple like 20 years ago over exactly this issue. What do you consider part of OS? What are you allowed to bundle versus not? And then below OS, of course, there's hardware, and that's tangible. That means you can touch, you can smell, you can weigh it, you can shake it. Right? That's the real thing. It's a physical machine, right? Including the computing units, including the storage units. It could be the memory, could be disk, could be other storage form, and also communication capability used to be all wired, now Wi-Fi. And other input-output systems could be keyboard, mouse, touchscreen, and other user interface displays. Okay, so this is a simple view of what a computer system looks like. On the bottom you have hardware, that's the real thing that runs things, and OS is the layer that kind of wraps around hardware. So programmers don't have to touch or program the hardware directly. They write code to call services provided by the OS. And OS decides how it's going to process the request. So that's the job of OS. But in this course, we're going to first take away the OS and let you write directly to hardware so that you get a sense of what it's like. And that's what writing assembly oftentimes is about. You actually get to control that hardware. And you get to play with the hardware directly by writing assembly code without OS, and you see how efficient it could be. Then we start adding this OS layer, and then you can see how much work it takes for the OS to handle this. And this is a relatively simple one. Okay. Then you can appreciate the OS because it makes your program much nicer to write. Writing directly in assembly can be fun, but at some point your code becomes very hard to maintain. And in addition to just low-level services, these services build on each other. And so you have systems programs, including your shell, right? You have bash or other shell you type in for command line. Anytime you write you want to start a program, a loader has to bring in the program memory, program image into memory, then it runs. There's a loader, you probably didn't know that it was there. Yes, it's actually called by the shell. So if you type ls, you type vim, you type make, you type something, somebody loads that program from disk to memory, then runs. That's a loader, okay? There may be backup programs that run in the background, like every hour, every day, every month or something. So there's these things that are used really at the system level because they serve the entire system. These are called system programs. And are they part of OS? Well, not the core part, not the kernel part, but they are tightly associated with the OS, right? And then there's, of course, these applications program, your text editor. Shell, strictly speaking, is or can be an application program. Your graphical shell, so user interface, well, that's another form of a shell too, right? It just happens to render it in graphical form. You can touch, you can use mouse, you can use touch screen, things like that. A compiler is part of OS, usually not considered it. But a compiler does provide libraries that you can link with, and then it works with the particular target platform. But you can have cross-compilers, and that's what we'll be using a lot. That is to cross-compile. You compile on a separate machine, right, and then targets a different machine. So general users are probably your consumer or what you might call typical computer user. For them, convenience or ease of use is more important. Good performance could be good. Not crashing is good, but if it's a user's program that crashes, well, OS can't do anything about it other than making sure it doesn't damage the rest of the system. But at least if it supports some kind of debugging, yeah, then it may be useful for the OS to give back some report. And so that the user can look at the crash log and see, oh, I had a bug this place, and helps them debug that way. And that's something OS could support. It doesn't require OS to support it, but OS could support it. And shared computers. So I remember when I was a student, we all had accounts on the same machine. We all logged into the same machine. Nowadays, you probably don't do this as much anymore, but you more likely use a cloud. Right? You have an account, and you should have your gap account. And remember, this is just a reminder, don't send me access requests for the materials posted in this course. Otherwise, you get 2 points off your course grade. Okay, so get your gap account and then authenticate and log in. So anyway, that's a different kind of shared machine. Before, we were sharing machine on one single refrigerator-sized machine. You log into that machine in text mode, and at the same time, we could have like 100, 200 people in the same class sharing. And there, what are considerations? Well, one, certainly protection. I don't want my other classmates to read my files and just turn it in as theirs, right? So that kind of protection is certainly needed. At the same time, I want it to be responsive, because imagine 100 users, homework due 10 o'clock, and they all try to get their assignments done. Compile giant programs. And then you type a key. I remember typing a key and then sitting there. 10 seconds later, it shows up. Right? So that's not very responsive. And of course, computers have improved in responsiveness. So even if it's not doing completing your job because it has to share with so many users, at least responsiveness is nice in that you type a key, it shows up, right, quickly. That's responsiveness. Throughput, on the other hand, more has to do with if a lot of users all try to do their job, and what is one way for the computer to schedule so that it can get the most jobs completed in the same amount of time? You might say, hey, how is that possible? I mean, the computer can do only so much work, and I put in this much work in there, and shouldn't it be the same amount of time from start to finish, no matter which order it does? Well, think again. There's an issue called I/O, input and output, and it can do scheduling. And I mentioned this last time too. So if you don't take advantage of overlap between I/O and computation, then what happens is it could just be sitting there wasting away cycles and then not doing anything. But if it's clever with scheduling, then it can overlap computation with I/O. That way, it can improve your throughput. So overall, everybody wins. All right. So throughput is something that can be improved by clever scheduling, especially with overlapping between I/O and computation. Now, for mobile users, the requirements are different. They want something that's friendly, easy to use, touch, precise, a nice interface, and most of all, they care about battery life, right? You don't want to have to use it for a few hours. Oh no, do I find a charger to charge it, right? Or carry a big power bank. That's not very convenient. Having a good battery life is good for mobile users. Now, for embedded computers, well, these things may have to interact with machines, mechanical parts, where timing may be important. So meeting timing constraints could be an important thing. And of course, power could be one if it's battery powered. So there's different considerations. Heating could be another thing that's related to power. So you don't want something that's wearable then starts to overheat and burn you, right? So that could happen. And certainly for phones, you've seen the cases where phone catches fire in your pocket. That's not good, right? So sometimes that's not an OS's problem, but OS could do something about it because modern computing devices can contain temperature sensors. They can throttle their execution. They know how much load they're carrying. They know the temperature. They should have a way to control it and not blow up. But sometimes the battery blows and OS can't do anything about it, right? So anyway, so now definition of OS certainly has evolved over time, but what has stayed constant is that the role of a resource manager and a resource allocator. Well, allocation is part of management. What does management mean? That means if you want to do something, you can't just go ahead and use it, you being the application program. I want this big chunk of memory. Well, are you allowed that? Well, the way an OS works is you send the request through the OS decides. Yes, you may have this chunk of memory. No, I only give you this chunk. Take it or leave it, right? So OS does the management. Why? Because it has to be fair to other users. It has to consider other things. Does it really have that much memory? How much is already in use? How much do you get to use at a time? Or it may make certain promises and say, okay, logically I give you this big chunk, but physically I only give you that little chunk. And because most likely you're only going to use a little bit at a time. And then if you're going to use more, well, anytime you use the part that I haven't really given you, I only logically assigned, but I haven't physically assigned to you, then it does a trap back to OS. OS says, okay, well, I need to fix this up. Maybe you kick out somebody else, grab out the memory, then give it to you, right? That happens a lot with the mobile, right? A lot of mobile apps you can open and then it opens up and it thinks it has all the memory in the world, but maybe you have 10 other apps already open. What happens? Well, OS could steal memory back from those other apps that are not running, right? You might have something else you put behind in the background. What happens to them? Well, logically they're still running, but physically they might be running on a slower speed. Maybe they're in sleep mode. And if a new app is running, OS could say, hey, I know you're sleeping or you're in the background. I'm going to take memory away from you. And a lot of times the app writer has no choice but, okay, fine. I'm in background. Here, give you back the memory. That's why sometimes you switch back to an app. Oh, it's right there. Other times it refreshes, right? It takes a little while because its memory was already taken back by the OS and it has to reload, reconstruct its data. So that's what an OS's job is, or part of what it does is it manages the resources, including memory, including CPU, time, storage, and part of it is really so that it can satisfy the request for as many applications as possible, at the same time offer protection, right? So protection means I have this thing running, you better not trash my other thing. I mean, why? Because they're sharing the same resources, and if you don't protect them, who knows, right? I mean, I can easily name an address space or the same address space with some other memory location. I have no idea. It could be a bug in my program. I dereference a bad pointer, and now suddenly it's trashing somebody else's memory, right? That's not good. So offering protection is a part of what it has to do. It has the goals of ensuring efficiency, fairness. Everybody gets a chance to execute, or at least the foreground probably should get more. That's fair, right? Security, protection. And part of what it does in managing is doing the control of the execution. So oftentimes called scheduling. So you have things to do, and what do you do? Do you give the foreground process all the time and background process none of the time? Well, that's not right, because you might be downloading your app, updating your system in the background. So if it's not in the background, should it just stop updating? I don't think so. It should continue updating too, right? So how do you ensure that foreground part? I mean, the foreground part might just be staring at some text, my notes, and not doing anything, right? So, well, that's a chance for the CPU to steal cycles, give it to somebody else so that it can keep running, right? Even if they're in the background, right? So. And also it has to do with I/O devices. So like your network interface, that's a form of I/O device, right? It could be doing your system update or app update over the network, or there may be other devices like you have a keyboard, mouse, stylus, things like that, right? So it needs to also control these things. So as part of doing that, it needs to prevent errors. And prevent improper use. Multitasking OS has the additional job of supporting multiple users and then manage resources, like I was saying, loading, unloading, even if not explicitly requested, right? It could be implied, it could be inferred, and it does what it thinks it makes sense. Scheduling program execution. And part of supporting multitasking also is to provide an API. API stands for Application Programming Interfaces. And so that means if you want to do something, you better make a function call. And these calls, if they're calls to the system, they're called system calls, right? So your printf in C program is not exactly a system call, but at some point it calls down to something that turns into a system call. That's when it actually turns into an input-output, well, output in this case. So printf does have user-level code wrapping around, but then at some point, yeah, it goes to the system, and then because the system has to control input-output, right? So these are calls at the low level, really entry point for the user to make requests to the system services. And the system can decide, okay, well, you make the request, fine, I'll decide how to handle it. It can deny it too. And so, for example, if you try to open the file and you run out of space already, it doesn't have to service that request. It can throw an exception back to you and say, sorry, it doesn't work. Or if you try to read somebody else's file, you don't have the permission. Again, it can deny you, okay? So the OS is kind of this guardian of the resources. You make function calls or system calls to it, and that's when it intercepts these illegal requests and can deny or allow. Okay, so that's much better than if you just were directly allowed to access that resource without a kind of a guardian right there. And this applies to user memory, I/O devices, storage, communication, a lot of things. So a general purpose program is sitting above, right? It's usually made by a compiler, or you could have an interpreter too. But whatever it does, what it does is there's a linker that generates the executable image. How does it do it? Well, you have user code, your hello world, but then when it does the printf, well, that you didn't write the printf code. That's taken from a library, right? And the library, the printf code calls something else. Ultimately, there is a system call or one or more system calls, right? And then that's taken from system library. So that gets linked in to your executable. Sometimes these are linked dynamically, other times statically. But it doesn't matter, the idea is still the same, that there is an interface. So when your code starts running and hits printf, goes to printf and down, ultimately it turns into what's called a trap instruction, which is a system call. Goes into the OS, and the OS handles it, handles the input and output part, right? Okay, so and then it goes down and then ultimately in the OS. But it has to be done in a controlled manner. You don't just say, I'm jumping to this address of OS. No, it has to be done in a controlled way, at least in a protected OS. Okay, and the OS then will decide, okay, what's this request? Do I allow it? Checks lots of things, and then says, okay, granted. And then it goes and schedule things. It makes it happen. When it's done, returns or sends a notification, whichever, right? And at some level, the device driver talks to the hardware and makes things happen. So where is the boundary of an OS? Well, we know for sure a kernel is part of an OS. That's always been the case. Kernel is the core part of the OS. And that means it's the part that is started when the computer boots, well, the bootloader loads it in, loads in the OS, and that's what's running, even if you're not doing anything else. And it has the control over the resources. Now, you can kind of grow outward and then say, okay, well, I'm offering shared services too. So at some point, you may need to decide based on whether it's running in kernel mode versus user mode. And we'll talk about that in a little bit. But there's at least a core part where it has to run in privileged mode. And these are things that user code could not do. But part of what people may claim to be OS could actually run in user mode. But that's only a rough guideline, because you have these microkernels where part of OS actually runs in user mode, right? So, but that's a different discussion. But my point here is that certainly the core part that runs in privileged mode or kernel mode, that's a core part of OS, no contention there. But you may have boundaries that are debatable. Now, there's something called bootloader. Now, is bootloader part of OS? It's certainly related, but strictly speaking, it's not. What's a bootloader? So when you have just a computer, right, and you power it on, what happens? There's no OS, right? So there's firmware. What's firmware? Firmware is program written in what's called non-volatile memory. It could be double EEPROM, could be flash, could be something, right? It could be even one-time programmable. So hard memory. In other words, its content sticks around even if you power off, right? It's still code, but what happens is your processor on power up knows where to jump to on power up. Sometimes location 0, and that's the case with 8051. Sometimes it's another location, but it's a known location. And that memory location is wired up with the processor. So that on power up, it jumps to that firmware location, and it can start running. But what does it run? Well, it runs the bootloader. What does the bootloader do? Well, it runs code, very much like our EdSim. It can run code, but what it does is its job is to set up enough so that it can load in the actual OS. It itself is not the OS, but it can load it in. How does it load it in? Well, it has to know probably how to talk to a disk at maybe a different level. It doesn't have to be full-featured disk driver, just enough. Or it could be over the network. It could do net booting too. So it probably has to support some kind of network protocol. Whatever it is, or it could display. A lot of times you may have, I'll show you in a little bit, right? So later I'll show you. On your PC, sometimes you have multi-boot, right? You can have Windows, Linux, whatever, different versions of Linux, Mac, right? You can select on boot up. Well, that's a bootloader. It offers you the boot up option, potentially. But if you have single boot, then, well, still there's a bootloader, it just doesn't offer you the option, right? So at least it's the program that's resident and does enough so that it loads in part of the OS, then the OS can load in enough of it to load in the rest of itself. So it's called a bootstrapping process. Loads in enough to bring in more functions, and that function allows you to load in even more functions, and then you build up that way. Okay, so that's the bootloading process. And the bootloader is usually not considered part of the OS, but it's closely related. And so that's the essential part for getting your OS up and running. Now once the OS is loaded, what happens? Well, it has to have certain things. One is called a program loader, as I was saying. A program loader is for the OS to bring in a program from, whether it's disk, over the network, whatever, into memory so it can start running. Right? And then it may have interpreters, or it may not. So interpreter would be your shell, like a command line interface, like a BASIC or DOS. Right? BASIC is an interpreter in the old days. A graphical user interface, right? Your Windows, iOS, Mac OS. You could even have like a Java interpreter. And then compiler and linker are not required, but oftentimes they're also there. Device drivers, yes, you have to have some kind of device driver, even if they're not a separate part. Maybe some libraries so that you can offer an interface for application programs to call in to the OS service. Now, as systems get more complex, concept of middleware gets introduced. What's middleware? Well, middleware is, you might say, things above OS level, or at least core OS level, but it is general enough so that many programs can be developed on top of it for easy. So it's really, middleware is meant for supporting developers so that they can develop their applications much more easily, or even users. So now web browser is kind of considered a middleware. Why? Because you can write JavaScript, you can for some time write even HTML5, Java, applet, and things like that. So yeah, in a sense, it's meant for developers to develop at a higher level. And so 1990s, Microsoft got into trouble for using their OS leverage to bundle IE. And that was considered anti-competitive because at the time there were other browsers, right, trying to get into the market, and Windows bundled Internet Explorer and did all sorts of tricks, and they got sued, and they said IE is an inseparable part of Windows. Really? Nah, I don't think so. but people got into this debate, and Microsoft kept arguing. And they say, yeah, you could remove IE app, but then the IE function is in Windows too. And people didn't really buy that argument. And in the end, they lost the lawsuit. But they didn't matter because their competitors got killed long before that the lawsuit was over. Anyway, so middleware is an example where people could claim that is part of OS too, even though it's not the core part of OS. Why? Because it supports developers, and developers have lots of power, right? And if you develop apps, you get more users, right? Now, databases, oftentimes considered part of, you might call middleware, and a lot of OSs are bundled, but they're not a core part because if you remove your database and put in a new one, yeah, that OS can still function. But the databases oftentimes are used by your application programs, right? And also multimedia service, cloud drive, location service. I mean, these are not essential, but as you build up more sophisticated applications, you don't want to reinvent these things. That's why they get factored out into middleware. And then application developers have an easier time reusing these services as opposed to reinventing these services, right? And of course, because OS is powerful, and if you offer these services powerful, the OS vendors like to include them, right? And that's why they keep drawing the boundary, because that gives them more power. Okay. Goal of OS, we talked about this a little bit, convenience, make the computer system easier to use and to program. So program, that's for developers. And now convenience is especially true for the smaller computer systems. And it's a desirable feature and helps you sell lots of units, even though technically not essential to a computer system. Efficiency certainly is desirable because you want to do the same amount of work in a shorter amount of time using less resources, less power, and so forth. Right? And so efficiency could matter more maybe on a larger system, multi-user timeshare system, and even mobiles too. But efficiency and convenience could be contradictory because for convenience you may have to do more work and that's less efficient. And OS, so one important concept is system API or application programming interface. Now API is a general term, so you can have certainly user level API, your MATLAB or the math library, scientific computing, machine learning API. But here we're talking about system API, that is the call into the OS to request the OS do something for you, to allocate memory, to open up a port, to allocate disk space, to access anything, right? Any I/O that your printf, right, ultimately goes to a machine API, standard I/O, file I/O, TCP/IP, right? And these things have better be all correct, shouldn't have bugs, because that's really bad user experience. If not even worse, you cause losses in productivity, losses in privacy. That's just not good. Data corruption, and in real-time systems or mission-critical systems, or in your self-driving car, it could crash. Right? So you certainly don't want bugs in those systems. And so it's important for the OS to be really robust, really bug-free, crash-proof. That hasn't been the case for a long time. Since the beginning of personal computers, they didn't have memory protection from the beginning. It took over a decade for that to happen. In fact, early PCs didn't offer protection. The 8086 didn't have memory protection. Even 286 didn't. It's until the 386 came. That's quite some time later that started offering some memory protection, right? And that required hardware to do this. Just in software you can't. You do need hardware to support. So OS and architecture do influence each other. You have OS provide service, but then there's things OS can't do. So hardware people say, hey, we can help. We add the new features, and then OS takes advantage of the new features. And then OS can do more, and then figures out it has these limitations. Okay, then hardware people add more features to support OS. Right? So they influence each other a lot. And also programming languages, new ones come out too. And so should it be supported by the OS? Should it be supported by architecture? Both? Well, that has always been an interesting question. But programming languages do have some influence, but maybe less so compared to OS on the architecture. So a computer system is organized in terms of one or more processors. Sometimes it looks like one chip, but there are multiple cores inside. Device controllers. Now the term device controller refer to hardware controllers that the processor can talk to, then the device controller talks to the actual I/O devices. Okay, and there's interconnect of CPUs, devices, and memory on what's called a system bus. So the line, the horizontal line that goes to the memory, CPU, disk controller, USB controller, graphic adapter, that's the system bus. And the bus may have hierarchy, so you can have tiers of buses. Slower devices, they may be isolated, and then the higher speed things may be on a different bus. Now embedded systems can have a different kind of bus too. The goal is to allow what's called concurrent execution of processor or CPU and devices. And see, the thing is, the memory is that thing hanging on the bottom. That means it's not just the CPU that has to touch memory. Your devices may also touch memory too. Say, really? I didn't know that. Yes, devices can read and write memory, can share the memory with the processor as well. And we'll see some examples. Okay, so let's start from beginning. So this is bootstrapping. So I talked about the bootloader, right? So on powering up, the CPU initial programming firmware is the bootloader. And so you may have seen this case. Or if you configure your Windows, do you want to start Ubuntu or Windows 10 or some other OS, Solaris, right? And so that's displayed by your bootloader. So it doesn't have all the features. It has only enough for you to make selections. So your mouse might not work completely, might only have to use up and down key because it doesn't have all that features, or it doesn't think you need that features, right? Those features. But it's enough so that then you can load in the next piece, add more features. Maybe it starts supporting mouse, maybe it starts supporting more colorful display, overlapping. This has no overlapping window. This is just probably some bitmap images, right? Or maybe it can do even lower level. You may have seen the bottom screen. That's ugly bitmap text, right? Well, that was the case in the older days when displays were text mode display, not graphical displays. And so the display itself knows how to draw the characters, and it draws those low resolution blocky characters, right? Anyway, the bootloader may also allow you to do a few additional settings like your default OS, whether or not it should show up, what key do you hold down to bring up this bootloader screen, right? The firmware can save those settings and then can detect, right, on if you hold this key combination, it goes to this mode, right? So that's what the bootloader may do. And once you make a selection, then what it does is does enough to read the part of OS image anyway. It might not be the complete OS image, but part of it, enough of it into memory, then jumps to it. Then once it jumps to it, it's out of the way. Then it's the OS that's running. Okay, and then the OS says, "Oh, I just got loaded," and it can realize, "Oh, there's some additional part I need to load in." Then it contains enough code to bring in more code into other parts of memory. And then it builds itself up. So that's the bootstrapping process, right? And part of what it has to do is really figure out how to talk to these devices. And in this course, yes, on the 8051, you'll get to talk to some devices too. You can talk directly, or you could isolate the functionality into device driver. So device driver is a piece of software whose job is just to talk to the device controller, right? And so device controller may be designed for a specific type of device. And for different devices, you may have the same controller or different controllers. And logically speaking, it is outside the processor. It's not part of your instruction set. But with microcontrollers or recent controllers, they may have certain registers that are associated with certain device controllers. So that if you read or write these certain memory locations, these registers causes side effects to happen to these device controllers. Why? Just because it's an efficient way to handle it. Otherwise, what does it have to do? The processor, CPU there, has to do a bus transaction, and then so it reads, writes a bus, device controller sits on the same bus, looks at the bus transaction, says, is the command for me? CPU talking to me? Yes, okay, then it pays attention. And then it has to decode the command, and these commands tend to be, are you reading or writing certain registers? And these registers have special meanings, right? So these registers may be the command word, so like go to this sector on this disk, or start reading, fill in this memory buffer. The memory buffer should start at this address, or it should end there, read how many bytes, the parameters, right? So these are in formats specific to the device controller, the hardware. And so device driver, which is the software side that understands the format, then would take care of the communication, packaging things up in the format that device controller understands. And then when the device controller responds, also over the bus, then it decodes it, and then so that sends it back to the OS, and the OS then treats them in a more uniform fashion. So the CPU, through device drivers, reads and writes these device controllers over the bus. And then device controller, once it has the commands, then it goes off and then does its own thing with the device. Then the CPU doesn't get involved at that point. Now, these devices may be slow. It may take milliseconds, sometimes much longer for it to complete an I/O. And so does the CPU just sit there and wait? No, not likely. I mean, you could, but that's a bad use of your resource, right? So that's why there's these notifications in the form of interrupts. Okay. Now, you could certainly do what's called polling. So CPU can say, "Hey, are you ready?" Sends out a different transaction and ask device, and then device controllers says, "No, I'm not ready," and sends back. But then that's wasted cycle over the bus. The more efficient way would be to have a wire from device controller to the processor into an interrupt line. So when the device finishes whatever it's doing, it asserts that interrupt line. I mean, logically you think it's set it to 1, but most likely it's asserted to active low. You pull it down. And then it's sometimes called IRQ. And so in older Windows, you might see IRQ error, IRQ conflict. IRQ, what's IRQ? Interrupt request. Okay, so that is a way for the device controller to notify the processor and say, "Hey, I'm ready. Come and get me." Okay, and then the CPU can then respond. How does it do? Well, it can just go to an interrupt service routine. But let's look at polling first. Polling is the simplest way to do it. Why? Because all you do is just treat it as another command. You can send command to device. You can certainly query the device controller. Are you ready? Read a bit. Gets a bit back. So in your loop, you can while the bit value. And the bit value, you can, in this case, this is the 8051. RI is the ready flag, right? Receive interrupt flag. But it's really not configured as an interrupt. It's a special function register tied to the device controller. So in 8051, very easy. You just read that bit. And you can do a while, not RI, do nothing. One line in C, very simple. In fact, in assembly, you can do that in one line as well. But why is it a bad idea? Because you're not doing anything. You're just wasting the cycle away, waiting for that bit to get ready. And that's really bad, especially for like if you're waiting just for a user to type a byte, a key, right? In the meantime, while it's waiting, can't do anything, right? That's really bad use. But at least it's deterministic. So yeah, you could do that. Or you don't have to do it in a type loop like that. You could have an if. If not RI, then go ahead and do other things. What's wrong with that? Well, certainly you can do that, but your code starts to get ugly, right? Because then just how often are you supposed to check it? I don't know. And if I'm running some other code, do I insert one every 10 instructions, every 100 instructions, every 1,000 instructions? I don't know. Your code then starts to get really ugly, right? And that's only one device. What if you have 10 devices? Do you pull individual ones? That just seems like a bad idea, right? Much better if it could be done by some kind of notification. That's where interrupt I/O is, and you'll get to play with interrupt I/O, and that interrupt I/O is an efficient way to handle systems and also to prevent a program that just hogs all the CPU time without ever making a system call, without yielding, and so forth. Okay, so busy waiting is inefficient. That's why interrupts get invented. And so that means the CPU just goes on and does its own work, including sleeping. Sleeping actually is more productive compared to just spinning like that, right? Because if it's just doing while loop, nothing, it's just sucking up power. At least sleeping, you save battery, right? So that's much better, right? So, and then an interrupt can wake it up if it supports sleep mode. So how does interrupt work? Well, it requires hardware to support this. So that means you declare some kind of routine called an interrupt service routine, or ISR. Sometimes people call it interrupt handler, but the formal term for it is interrupt service routine, ISR. Okay, you could call it interrupt handler, but ISR is really the proper term. So it's the hardware that makes the call. What hardware? CPU. So you're running along and then user presses a key, generates an interrupt. So the CPU suspends what it's doing in the user program, jumps to interrupt service routine, handles the I/O, and comes back. The user program didn't know it got interrupted. It just runs along, and logically speaking, it didn't see any difference. It just keeps running. Unbeknownst to the program, the CPU actually suspends it, does it handling the I/O, comes back to it in such a good way that the user program didn't know it got interrupted. Okay, it has no idea. It just keeps running. Of course, it's a lot of work on the CPU to present that illusion. When it interrupts it has to remember where the program was running. It has to save all of its registers. Because when you run code, you touch the registers. You trash the accumulator. You can ruin a lot of other things too, right? So it has to save a lot of things, and then it jumps to known location to handle the service. And then when it finishes, has to know where to go back to, well, restore everything so that the user program didn't know that it got interrupted. Okay, so this is more of a timing diagram for the user CPU, running user program, and then an interrupt could come in for different things. Could be for like in this case DMA. So that means you might have a block transfer. It could be in the case of network transfer, disk transfer, whatever, into memory. So upon completion, the I/O controller generates an interrupt, and then so that's where you see that dip. So the user program still runs along, but it jumps to the interrupt service routine to say, oh, you just completed the transfer, fine, okay. CPU in the interrupt service routine handles what it has to do, sets up user program whichever way, and then returns. The CPU returns from ISR, resumes normal execution, and maybe the next DMA cycle finishes, and then it interrupts the CPU, and then so this way the CPU doesn't have to get involved in the byte-to-byte transfer, doesn't have to worry about are you ready, that kind of thing. Just let the controller do its own thing. When it's done, gets notified, then handles it all at once. Okay, much more efficient this way. So the steps in interrupt-driven I/O, the processor calls device driver to initiate I/O, so talks to device controller. On the right side, that's a device controller hardware, initiates I/O, but then CPU continues executing, and then it does the check for interrupts between instructions. So your code doesn't have to do the actual instruction, interrupt checking. It's a processor that does it. Okay, and it checks interrupts only between instruction boundaries, right? Not within an instruction. And then it can do its own thing, and when the device is ready, sends an interrupt, and that happens between instruction boundaries. So in the pipeline processor, the processor has to kind of flush the pipeline. And then nothing else is running. That's when it saves the state, jumps to the interrupt service routine corresponding to that interrupt source, and then finishes what it's doing, restores the state, resumes the user program. Okay, so interrupt is an important part, actually essential part of modern OSs. They use interrupts not only for handling I/O, but also for many other things, for making sure context switch happens, and also there's things called software interrupt, and that's called a trap or system call. So it's handled in the same way as a hardware interrupt, except the trigger source is not from outside, but by executing a trap instruction, sometimes called a system call instruction or something else. Or it could be as part of executing an instruction, could be divide by zero or access memory that's out of range and things like that. Okay, so these are all possible ways to generate or cause a software interrupt, but the handling mechanism is all very similar. Okay, let's take a break here.